So the key to this, guys, is we have to understand which things are vector and which things are scalar. That is the entire point of this entire quiz. I know you guys can manipulate v equals d over t. I have absolutely no doubt in my mind about that. Okay? But what this quiz is asking is, do you remember that distance is scalar, velocity is vector, okay? Speed is scalar, because it makes a difference on how you calculate them in the question. All right? So for the first question, right, what we've got, first off, a mark for our givens. All right, so if they have the part 1 and part 2 stuff written down, okay, 2,500 meters north, 75 seconds, 18 meters per second south, and 55 seconds, okay, that's 1 mark. If I want to find the total distance traveled, I need to find the distance in part 2 because it wasn't given to me. All right, so that's our next step here. Okay, we're going to manipulate v equals d over t, d equals v times t. So that's going to be our 18 meters per second times 55 seconds, and that gives us 990 meters south. So that's actually the displacement, not the distance. But since it's a straight line, is the distance 990 meters? Yes. All right. So now I can find the total distance. I know it went 2,500 meters, and then it went 990 meters. Since distance is scalar, direction doesn't matter. I do what with those two numbers? Add them together. All right. So next mark then is for getting that the total distance traveled is 3,490 meters. All right, so we're up to 3 marks here. Okay, the next 2 marks are for calculating the average velocity. If I want average velocity, I need total displacement and total time, because displacement is vector and goes with velocity. So now, the fact that this 2,500 meters is north and this 990 meters is south becomes important. All right. So my next step then is that I have to go 2,500 minus 990 over the total time, 75 plus 55. So if they showed somewhere along the way, either they showed 1,510 over 130, or they showed this operation that I have here, either way, give them a mark if they knew that they had to subtract or add a negative there, okay, in order to get the total displacement. And then the 5th and final mark is that this is 11.6 meters per second north. They must have the north to get the mark for the answer. If they do not have the north, the answer is wrong because it is a vector quantity and must have a vector. Okay? Everybody with me there? All right? How important is it to know which ones are scalar and which ones are vector? It is crucial. Okay? Absolutely crucial. All right. Who's out of 5? So in running a line drill, if you play basketball, we sometimes call these suicides because you want to after you're done. Okay, you run to the foul line and back, center line back, opposite foul line back, baseline back, and usually we say you have to do it in under 27 seconds, which means you're like ready to vomit. Okay, now there's forward and backward. There's this vector thing that goes on there. All right, so they run forward 15 meters at 10 meters per second. Then they run backward 10 meters for 1.1 seconds. So we've got 3 different parts to this. So if they have the 3 parts and what we were given, give them a mark. Now, obviously, since in a proper line drill or suicide, you end up back on the baseline from which you started, your total displacement and total velocity would be what? 0, because you'd end up where you started. So the point of this question is to get you to calculate the total distance and the total time, which are both what kind of quantities? Scalar. All right. What we got to do then is figure out the total distance and the total time. I was not given the time for part 1. All right, I was only told that they went 15 meters at 10 meters per second. So I have to do a manipulation here. Okay, t equals d over v. Give them a mark if they did that, and that should come out to 1.5 seconds for part 1. I'm given all the other distances and times. So all I have to do now is add them all up. Okay, so my next mark, right, is going to be for v equals d over t, 15 plus 10 plus 15, because direction didn't matter, 1.5 plus 1.1 plus 1.6, okay, or maybe they just went 40 over 4.2, whichever, okay, give them the mark for that. And then your final answer is 9.52 meters per second. Yeah, if they have 9.5, that's fine as long as they have meters per second on there. All right. If they have a direction on there, it is unfortunately wrong because speed does not have direction. It is a scalar quantity. All right. Questions on any of those? So they're both out of 5. Quiz is out of 10. Please give them a mark out of 10. Let them see it. Put it in the box. Okay. So yesterday we did the graphing lab, okay, where we had the carts going down the hallway, right? And we made what kind of a graph from that? Okay, we made a linear graph. Okay, but what two things did we graph? Yeah, okay, time and distance, or sometimes we call that a position versus time graph because it shows us where the cart or object was at various points in time. All right, now, what did we say that we could get, or what were we asked to get in that lab from that graph? Velocity. Okay, we were asked to get velocity from that graph, and how did we get it? We used the slope of the line. All right, when you're using graphs, especially in science, especially in physics, okay, but I mean it is important in bio and chem. It becomes important to be able to look at a graph and figure out what you can get from that kind of graph. Okay, a lot of people in Science 10 will just, oh, I'm not going to take physics. I'm just going to memorize what I can get from each kind of graph. And while that might work for you in Science 10, in the end, when you get, if you take physics all the way through, or even in chemistry, whatever, if you don't have the skills to be able to look at a graph and interpret it and figure out what you can get from it, you're really going to struggle. Okay? Reason being, the diploma exam is full of graphs. Doesn't matter which science you take. Okay? They put graphs like crazy on the diploma exams in your grade 12 year, and they ask you to interpret them. Okay? And if you haven't been able to figure out, well, you know, if I calculate the slope, that's going to be this unit over this unit. Oh, those units are the units for whatever. Okay? It becomes more difficult for you because it becomes hard to analyze and interpret a graph. Okay? So interpretation of graphs and figuring out what the slope will give you, or you know, things like that, is really important. That's what we're going to go over today. We're only going to go over two kinds of graphs. Okay? We're going to go over the position versus time graph, like we made yesterday for the lab, and we're going to go over velocity versus time graphs. Okay? Now, on a velocity versus time graph, it's just like it sounds. It's showing you the velocity of the object, how fast it's going, okay, at various points in time. Everybody with me there? All right, so we're going to look at those and how to analyze them, or how to get certain kinds of information off of them. Reminder about the graphing lab. Okay? It is due November 27th. Okay? Remember that the only times you'll have to have me look that over are going to be today at lunch, tomorrow at lunch, or Monday at lunch. Okay, or in scheduled help any of those days, because we don't have school Friday. Thursday's a short day, so there's no scheduled help and no lunch hour. Okay, and I'm not here Tuesday. All right, so make sure that you see me if you want it looked over before then. Okay, questions on that? All right. You can still email it to me, but I'm going to be out of the country over the weekend. Okay, so you know, I'm not going to be looking at my phone very much because I don't want to pay the gargantuan data costs. And on the Tuesday, I'll be supervising people at West Edmonton Mall, so I don't know how much time I'll have to check my email that day either. So you can, but I can't guarantee that I'll get a look at it. Okay. All right, so key points for today. Understand what information can be read from kinematics graphs. Okay, understand the graphs and the equations that we use are derived from graphs. Okay, the equations that we use, okay, come from slope calculations of certain kinds of graphs and things like that. Now, I am going to give you your formula sheet here this week. I just haven't printed them yet, but I will get them to you. And yeah, so that's points 2 and 3 here. That kinematics graphs and equations showed the same information in different ways, and that we get those equations from graphs. Lovely. Okay. The purpose of a graph is essentially to tell us, or to show us, data in a more, let's say, efficient manner. Looking at a chart of data that's just numbers doesn't always tell you the full story. Okay? Or at least it's not as quick to tell you the full story. When you look at a graph, can you see what's going on? Okay, and that's the purpose of a graph, to represent data visually very quickly. All right, so if I'm looking at this graph here, this is a position versus time graph, the one on the left. All right, What can I tell happened with this object? What are some things that happened with this object? Anything? Okay, near the end, it went backwards a little bit. Okay, that's what this is showing. Its position went from 60 meters to 20 meters. Okay, the only way to do that would be to move backwards. Okay, what else happened? It stopped for a period of time. Okay, how do we know it was stopped there? The position didn't change. It was at the same place, 60 meters for a second and a half. All right, what else did it do? Kendra? Right, it traveled forward for a couple of seconds. Okay, and what did it do here? Yeah, it just sat there. Okay, for a second, didn't move. Right, it was at position 20 meters at time 0. It was at position 20 meters at time 1 second. All right, did it start at position 0? No, it did not. Okay, it started at position 20 meters. All right, so that's one of the skills we have to be able to do is look at a graph and figure out what was going on. All right, now how do we know, or sorry, not how do we know, what kind of movement happened in this section of the graph? Did it travel at a constant speed? Did it accelerate? Okay, travel at a constant speed. How do we know that? It's linear. Yeah, exactly. Okay, it's linear. If we look at it, in 1 second, it went from 20 to 40. That's 20 meters. In the next second, it did exactly the same thing. In 1 second, it went from 40 to 60 meters. All right, this is a linear thing because it is traveling at a constant speed of 20 meters per second. All right. Other things will be expected to possibly do with the position versus time graph. How far did this object go? Okay, 60 meters. All right, so it went up 40, and then it came back 40. It went 80 meters. Okay, how did I figure that out? Well, I went, okay, 60 minus 20 is 40. Okay, and 20 minus 60 is negative 40, but I only asked how far it went, so 40 plus 40 is 80. All right, what's the displacement of the object over the whole trip? 0, came back to position 20, that's where it started from. Okay, how did I figure that out? Well, I went final position minus initial position. They were the same place. Okay, we can do a lot of things. We can get a lot of things from a position time graph as long as we understand how to do it. Okay. What was the average speed of the object? Okay, how far did it go? 80 meters. How long did that take? 6 seconds. Okay, so 80 over 6, okay, should be, what, 15? Is that right? 13.3, okay, so 13.3 meters per second. Again, just use the graph. Okay, I got the data from the graph, and then from there I went back to this. Okay, it's okay to use the formulas with information you get from a graph. All right, and that's what we want to do. All right, so that's showing you some of the things you can see on a position versus time graph. What's going on in this position versus time graph? John? Right, it's accelerating away from the starting position. How do I know that it's going faster all the time? Okay, it's exponential, it's curved. Okay, what does the curve tell me? It tells me in the first second, okay, it went from 0 to whatever this is. It looks like 0 again, but okay. And then in the second it went from that point to 10. And then in the next one, it went from, well, not actually to 10 to 8. Okay, we'll say. Didn't get all the way to 10. In the next second, it went from 8 to, what, 18. Right? Is it going faster? It went only 8 meters in the first one. In the next one, it went 10. If it went 10 meters in the same interval of time as it went 8 seconds, it must be going faster. Okay, it's covering more distance than it did the second before. That means it's speeding up. Anytime an object is speeding up, this is the shape of the position versus time graph. Okay, the steeper the curve, the faster it's accelerating. Right? Does that make sense? Can I calculate the slope of a curve? No. The slope of a curve is always changing. That's why it's a curve. All right. A line has a constant slope, but a curve is many small straight lines strung together, all getting steeper. Okay. All right. So position versus time graphs, like we said, are used to represent the location of an object. Okay. Location of a moving object over the course of time. Okay. So we can read displacement directly off the graph. Okay, so that's one of the things we can get off of these. We can read displacement right off of this graph by going final position minus initial position. Okay, we also said that we could get distance off of these graphs. And how did we do that? How did we figure out how far this thing went in total? Right, did we figure out how far it went in each section? Then what did we do? We added them up, okay? So to calculate the total distance traveled, okay, you total all sections. Okay, total all sections of the graph, regardless of direction, obviously. Okay. Okay. You can get, if it's just one section, it doesn't have many sections, you can get velocity by calculating the, okay, by doing distance over time, but if it's only got one section, that's actually calculating the what of the line? Slope of the line, right? Okay, yes, in a graph like this, we would have to do total displacement over total time because there's many sections, all right? But on a graph that has just one section, okay, we would use the slope, okay? So little things to remember there. Very often, guys, on this unit exam and on the final, I put graphs on there, okay? I put in the multiple choice, in the written response, and I just say, get the following things from this graph, okay? Or using this graph, get this information for me, right? And so you have to show me how you go about doing that. This also tends to be the thing people study the least and thus do the worst on my unit exams. Okay, so this is something you definitely need to go over because there's lots of marks to do with this. Okay, especially in my class because I teach Physics 20 and I want to make sure that everybody who gets there knows how to do this, right? Because it's so important. So know that I emphasize graphs and interpretation of graphs a lot. Okay, last year Physics 30 diploma exam, of the 50 questions on it, 19 involve graphs. Okay, so it's a big deal. Being able to interpret graphs is a big deal. Okay, and I know there were several on the chem and there were 4 or 5 on the bio. Okay, so it's a big section of your mark. Okay, we got to be able to interpret graphs. All right, slope calculations, just quick review. We already know how to do that. Okay, slope is rise over run. Okay, on a position versus time graph, okay, when we calculate the slope, are we essentially taking the final position minus the initial position over time? Yeah, that's what we're doing, right? Okay, final position minus initial position over time, which just happens to be on a position versus time graph. The change in displacement or change in distance, depending on what kind of graph it is, okay, over time. Over the change in time. Remember delta, that little triangle means change, all right? So anytime you see delta, it means final minus initial. All right, so on a position versus time graph, okay, the slope of the line will give you velocity. On a distance versus time graph, the slope of the line will give you speed. Okay? Now, most of the time we'll be dealing with position versus time graphs. You very rarely actually draw strictly distance versus time graph. All right, everybody's good with that? Slope on a position versus time graph gives you velocity. That's got to be automatic soon. Okay? All right. This is a position versus time graph as well. Except this one shows the object going into the negative positions, which means essentially like this. If I start right here directly in front of the center of the smartboard, okay, the object went this way and then stopped, and then did what? Went backwards, past where it started, over to here, and then stopped, and then did what? Went forwards, okay? But it went forwards in two different sections there. What's the difference between E and F? Right, the speed at which it traveled, or the velocity in this case, at which it traveled, okay? Which one's faster, E or F? Right, because it's steeper, okay? Covered more distance in a shorter space of time, or the same distance in a shorter space of time. Either way, okay, it went faster during part E than it did in part F. All right, and guys, honestly, last year on the unit exam, I put a graph like this and asked simply that. Tell me what is going on in each section. Okay, so in part A, I'd be looking for the object was traveling forwards at a constant velocity. Okay, is that what's going on in A? Okay, what's going on in B? The object is stopped. Okay, what's going on in C? At a constant velocity. Okay, and I know that seems nitpicky, but if you said backwards, you can't say backwards and say speed, because you gave a direction and speed doesn't have direction. Everybody follow? Okay, and that's all I'd be looking for. That question was the worst done question on the entire exam, believe it or not. Okay, people could not look at the graph and tell me what was going on. All right, and I had a graph. It was essentially, it ended here, I think, something like that. You know what everyone told me it was doing in C? Take a wild stab. What did they tell me was going on in C? Yep, that's what they said. It's speeding up. They also told me that's what was happening in A, because we see this line that's going up and immediately think something's increasing. But for some reason we default to speed. Something is increasing. What is it? It's displacement. Okay? Its displacement is getting bigger. All right? Its displacement is changing. That's why the line is going up. The most important part of getting a question like this right is looking at the axis. All right? This is not showing a change in speed. It is showing a change in position, which is displacement. Okay? Really crucial that we can understand that. The most important part of a graph, and this is why we said you have to have these on a graph, are the labels and units on the axes. If we don't have those, there is no way to interpret the graph. Okay? Or we'll interpret it wrong. All right. Let me phrase another question here, because I've done stuff like this on quizzes and tests before too. What is the displacement of the object between 0 and 6 seconds? Nathan? 6. Forward. Right. Yeah, ask for displacement. See, and that's where people get caught. On a quiz or a test, they're like, oh, it's 6. Boom, 6. And that's all they write is 6, and they get nothing for it because they don't have any units and they don't have any direction, and I asked for a vector quantity. Okay? So always be thinking, I asked for displacement. Displacement's vector, so forwards, positive something, okay? 6 meters forwards. All right? What's the velocity of the object between 0 and 6 seconds? Okay, where did it start? Okay, where did it end up? 6. Okay, what was its displacement between 0 and 6? 6 meters forwards. All right, how long did that take? Okay, what's its velocity? 1 meter per second forward. All right, so there's just those little details that we have to know, and that's why practicing your graphing stuff is so important. All right, let's say, what was the distance traveled between 0 and 10 seconds? The distance traveled between 0 and 10 seconds. I asked for distance. Is distance scalar or vector? It's scalar. Here? Well, we have the technology to figure that out. 10. Good, see? 22 meters. Yes. 6 plus 6 plus 10. Okay? So we have to figure out all the sections, right? We just wrote down 2 slides ago. Okay? Distance. Total all sections. So that's what we did here. Okay? We went 6 plus 6 plus 10 is 22. All right? 22 meters. Don't have to give a direction because they asked for distance. All right. What was the speed of the object over that same time? .2 meters per second. How do we know that? Well, we already told ourselves that the distance was 22 meters over 10 seconds. 2.2 meters per second. All right. Mathematically, are those calculations very difficult? No. Okay, it's adding, subtracting, doing a little bit of division. It's nothing hard. The tricky part is being able to interpret. Okay, he asked for distance. That's vector, or sorry, that's scalar. Okay, he asked for displacement. He asked for velocity. Keeping those straight is a big deal. All right, and because it influences how you use the graph. Is that making sense to people? All right. Sometimes you're going to get a graph that looks like this. It's still a position versus time graph, but there's curves all over it. Okay. Well, curves mean the object's velocity is changing. All right, and that's what it's doing here. So let's first interpret the graph. What is the object doing in section A here, where it's going up? Okay, it's increasing its velocity in a forwards or positive direction. Okay. What's it doing in section B there? It's stopping and okay, so it's decreasing its forwards velocity by increasing its backwards velocity. Okay, so actually what's going on in part B here is the object is slowing down, stopping, and then going the other way. Now it's accelerating backwards. Okay, that section of the graph would be a graph of this motion. Okay, as I fling the marker up in the air, it accelerates as long as it's in contact with my hand. As soon as it leaves my hand, it starts slowing down. It stops instantaneously at the top before it starts to fall back the other way and accelerate back down. Yeah, if you were talking about going over the top part of the hill, yes. Except that usually they don't stop, right? But yeah, vertically speaking, yes, it would be like that. All right. What if a question said to you, calculate the instantaneous velocity at point A? So here's point. Oh, come on. Here's point A. It wants me to find out, the question might say, find the instantaneous velocity at point A, or calculate how fast the object is going at point A. Well, normally, we would figure out velocity in one of two ways. V equals d over t, or slope. Well, this is a point. I can't really use v equals d over t here because it's accelerating, and v equals d over t is only used for an object traveling at a constant speed. So that's no good. And I can't find the slope of a curve because the slope of a curve is always doing what? Always changing. So here's what we have to understand. And I think you'll understand it. It was the only thing I understood in university calculus. I got through university calculus by memorizing all the examples in the textbook and writing them down on my final exam and getting part marks for method. I don't recommend that as a way for you to be successful, but it worked for me. I was in a class with a lot of really stupid people, including myself. Okay? Luckily, I was able to surf the curve in that class. Okay? Do you know what that means? They grade you on a curve. I was able to surf along with the average of the class because we were all equally stupid. All right? If you do calculus, figure out how to do it. Don't do it my way. Okay? All right. The only thing I understood in university calculus is this. A curve, to a mathematician, is an infinitely large number of infinitely small straight lines. Those straight lines are always getting steeper. Okay, that's what makes a curve. It's like if you look at like a low resolution picture on the internet. What can you see sometimes in a low resolution picture? You can see the pixels, all right? Because a computer makes smooth curves by making really small squares so small and so many of them that you can't see them all strung together, because a computer can only deal with 1 and 0. It's either off or it's on. Okay? And so that pixel is, if it's small enough, you don't see it. But if it's a low quality picture, the pixels are big and you can see all the squares. Well, it's the same with a curve. A curve is made up of a whole bunch of little squares or little lines that all get steeper. So what we need to do then, if we know that slope on this kind of graph is velocity, is calculate the slope of that infinitely small straight line that exists at point A. Well, there is a problem with that. It's infinitely small. Okay? How can I calculate the slope of an infinitely small line that is not going to cross at least 2 grid intersections? The answer is, I make it longer. And I do that by drawing a tangent line. Anybody know what a tangent is? Okay, what is a tangent? Right, it touches only one point on the curve and never crosses the curve. All right, it runs tangential to the curve. So if I want to draw a tangent line that will, well, I'll just, because I can cheat here. See, this is the beauty of the smartboard. Oh, I am a cheater. I fully admit. Told you guys I wasn't good at math on the very first day. Okay, so now I have a tangent line. I can make that line now as long as I want and make it cross grid intersections, hopefully. Okay. If not, it'll at least give me the opportunity to, yeah, I've got 2 grid intersections, right here and right here. All right, can I calculate the slope of that line now? Yep, and because it is parallel to the infinitely small straight line here, it has the same slope. So now I can calculate the instantaneous velocity, the speed at point A, by calculating the slope of that line. Are you going to be asked to do that very often in Science 10? No. All right, but you still need to know how to do it because it's one of the first things you're going to be asked to do in Physics 20. Okay, so it's just a way to reinforce that slope from this graph gives you distance over time, or displacement over time gives you velocity. Okay, the slope of a line on this graph is going to be velocity. All right, what's the velocity at point B? Okay, it's 0. All right, we can recognize that, but we can also prove it. We said to calculate the velocity on this kind of a graph when you have a curve is you calculate the slope of a line. Well, here's a tangential line at point B. It touches the curve at point B and never crosses it. What's the slope of that line? 0. It has no slope. It's horizontal. But it works, doesn't it? Okay. And I would do the same thing here for point C. They've kind of got them drawn in hashed marks here. All right. That line, okay, that they've got in the hashed mark that I'm going to follow in red here, all right, shows I could calculate the slope of that line and have the instantaneous velocity at point C. Okay. Again, just got to remember that if I'm using a position versus time graph, velocity can always be calculated with the slope of a line. It can also still always be calculated using total displacement over total time if we're talking about multiple sections of the graph. Okay? All right. Now, velocity time graphs. Okay? Velocity time graph tells us how fast and in what direction the object is going at various points in time. Okay, so it shows us essentially the progression of the object. Now, for some reason, my 2 graphs are missing here. Oh, sure, it didn't get it all. Oh, that's not what I want. Okay, now that I've got the graphs I want. These 2 graphs are showing exactly the same thing. Why do they look different? Right. One's a position versus time graph. The other's a velocity versus time graph. All right. The one on the left is showing the position of the object at various points in time. Now, looking at the shape of this graph, what is the object doing? Alicia? It is moving forwards at a constant velocity. Okay, moving forwards at a constant velocity. All right. A lot of people, if I gave you that on a test, would say the object is accelerating, but it is not. Okay, because it's not a curve, right? It's not curving, it's not accelerating. All right, so this is showing an object traveling at a constant speed. Could I figure out how fast it's going? Or sorry, at a constant velocity. Could I figure out how fast it's going? Yes, I can. Okay, by calculating the slope of this line. All right, so if I want to calculate slope, let's say I'm going to use that point and that point, just because they're convenient points and they're grid intersections. Okay, so this is going to be 1400 minus 100. Okay, over 5 minus 0. Okay, so that's going to be what, 265? 1300 over 5? Someone just punch that in real quick. 260? Okay. All right, so my velocity is 260 meters per second, and we'll say that's forward. All right, that's the velocity time graph of this motion. What is it showing? Right. It's showing the same thing, right? It's showing that the object's velocity is not doing what? It's not changing. All right. It is showing the object is traveling at a constant velocity of 260 meters per second the entire 5 seconds. Exactly the same thing this graph is showing. We're going to talk about that in a minute. Is that what you're going to ask too, John? Oh, that was just to indicate where the graph ended at 5 seconds. Yeah. All right, is that making sense to people? So they're showing the same thing, but they're showing it from different points of view. One's looking at where the object is, the other's looking at how fast the object is going, okay? And that's why they look different, okay? What if I had this velocity versus time graph, but instead it looked like this? What is that object doing? It's accelerating forwards. Okay, so now this position versus time graph doesn't look like a straight line anymore. It looks like a curve, right? So it would go up like this. All right. Now, what if my velocity versus time graph looked like that? Nope, not quite. Okay, it is moving forwards, but it is decreasing its velocity. That's a tricky one. Okay, how do I know it's still going forwards? Because its velocity is still what? It's still positive. All right, but a lot of people will look at this and say the object is going backwards. It isn't. It's accelerating backwards. That's what slowing down is. Okay, slowing down is accelerating backwards. All right, but it is still moving forwards. Right? When you slam on your brakes in the car, and this is why we as North Americans don't understand this properly, you are accelerating backwards. The reason we don't understand it correctly is because brakes will never make you go backwards. They just make you stop. All right? Because they rely on friction, and friction won't make you go backwards. You guys follow me there? Okay, so Terry was right on the ball there. Okay, this is an object moving forwards at an ever decreasing speed. All right, so what that looks like on the position versus time graph is this. Okay, it's showing a curve, but that curve is getting flatter and flatter and flatter until it approaches horizontal. Then it would actually be moving backwards. Okay, so let's say it went below, like this. Okay, so now it's moving backwards, and it's also accelerating still backwards, right? Because its velocity is still changing. It's going faster and faster now in a backwards direction. So this graph and starts going like this, right, and curving down the other way. Okay, does that make sense to everybody? So it's possible for your position versus time graph, or sorry, your velocity versus time graph to have negative values, but your position versus time graph to still be in the positive. Right? You were going forwards. Now you're accelerating backwards, but you still have to get back to where you started. Okay? Before your position will actually be negative. Right? So one like that would be pretty tricky. All right, is it making sense? Mac? Yep. Only this portion of it here is going backwards. The whole line is accelerating backwards. Okay, like because the velocities on this side, okay, here are positive, we're still moving forwards, but at an ever decreasing rate. Okay, and then here would be now I'm actually moving backwards at an at the same rate. Okay, but now so it would be kind of like if you were attached by like a bungee cord, okay, and you were running. Right? So you're running, there's slack in the cord, you're running, now the cord takes up, right? So you start slowing down, but you're still moving this way, but you slow down as the cord pulls you backwards until you can't pull the cord anymore. Right? You start moving backwards. You're still forward of where you started, right? But now you're actually moving in a backwards direction. Eventually you'll get fired back the other way. Yeah? All right. Velocity versus time graph of a person running a race. What's going on in the first part here? They're accelerating. Okay? They're changing their velocity. And in fact, there's even a little curved section here which says that their acceleration wasn't perfectly uniform, which is true. When you first start a race, you often aren't very uniform in your acceleration, but once you kind of get your pace going, then you do accelerate pretty linearly. All right, what's it doing here? Right, they've reached their maximum speed. They can't accelerate anymore, so they're maintaining a constant speed now. All right, their meters per second is staying at around 8, right, for the next few seconds. And then, what about this part? Right, they've crossed the line and now they're slowing down, and eventually even coming to a stop. Because notice, the line gets all the way back down to 0, and when we reach 0, it means our velocity is now 0, and thus we have stopped. Okay. Everybody good with that one? Okay. All right, so just some quick stuff here. What you can get from a velocity versus time graph. Obviously, you can always tell how fast the object is going. That's what this first part says. The vertical value of any point is the instantaneous velocity at that time, so how fast the object's going. You can read that directly off the graph. Okay. One of the other things we can get from a velocity versus time graph is acceleration. Okay. Acceleration is the rate of change of your velocity. So if I've got a velocity versus time graph that looks like this, we've said that object is accelerating. Okay, I can calculate the rate it changes its velocity at by calculating the slope of the line. Okay, because the acceleration is the rate of change of velocity. So y2 would be your final velocity, y2 would be your initial velocity over time. Okay, so you get your acceleration. I'm not going to go too much into that right now because we haven't talked about acceleration yet. We'll come back to that when we talk about acceleration. Okay, the other thing you can get from a velocity versus time graph is displacement. Okay, the area underneath the line, okay, on a velocity time graph is equal to the displacement of the object. Okay, so I'm just going to go back here a couple of slides. How far does this object go in the 5 seconds it's moving? Chase? Okay, no. Nope. Okay, we just said the displacement of the object is the area underneath the line on this graph, right? Okay, so That's going to be 260 times 5, right? Base times height. That's how we find the area of a rectangle, right? Okay, base times height. So 260 times 5, and I know what Jace was doing here. He was cheating, and he was looking at the position versus time graph and trying to figure out how much there was. Well, what's 260 times 5? I think it's 1,300, right? Is it? 1,300. Well, what's 1,400 minus 100? 1,300, okay? Final position minus initial position will also get you displacement. Now, if you look at this graph here, I just went base, which is time, times height, which is velocity. Same thing? Okay, that's why that formula works. That formula was derived from graphs. Okay, we know that that relationship holds true. All right, so now that's easy enough if you've got a rectangle, space times height. What if you're given a velocity versus time graph that looks like that? How do you find the area of a triangle? Base times height divided by 2. Okay, it'll still work. All right, essentially what it's doing is it's taking the average velocity, okay, and multiplying it by time, because half the time you were going slower than that, and half the time you were going faster than that. Okay, so if you take the average and multiply it by the total time, you'll have the total distance traveled. Okay, now, what if I have a graph that looks like this? Right. It's still the area under the line. The area under the line is still the displacement. It's just now I have 3 shapes to calculate the area of. All right, so I calculate the area of this triangle here, of this rectangle, and this triangle, and then do what? Add them all up. Okay. All right. One last thing. What if? Whoop. That's supposed to be one straight line there, guys. Okay. What if I had this and then it went like that? John? Right. Still the same rule. Find the area of all the sections, but remember that the sections below the x-axis have areas that are negative. All right? Because they would have, like, let's say it's negative 200 down here. Okay, well, negative 200 times, okay, whatever it is there, right, gives you a negative number. It still holds true. The area, and I know it's not under the line anymore, but it's between the line and the x-axis, so we say under the line. Okay, add them up, and you've got the total displacement. Okay, that is the one I ask most often on a test as a question asking, do you remember what you can get from the types of graphs that people do wrong? No, I will not, because you haven't done any differential calculus. And I can't. And I don't know how. Okay, remember, I'm the guy who memorized the examples in the textbook to get through calculus. I will not ask you to do anything I am not capable of doing, especially since you're only in Science 10. All right. Okay, so that covers most of it. Now, on the handout I gave you the other day with all the different graphs, okay, there was some questions there. Yes, the one here on the very last page, okay, that has the this graph here. Okay, I want you guys to try questions 1 through 4 using this graph, keeping in mind it is a position versus time graph. All right, it's a position versus time graph, so I want you to use what we learned today in the next 5 minutes here, okay, to calculate or to do as many of these as you can, and we'll use that as our starting point for tomorrow's class. Question?